welcome to the Academy. This is a video that's part of a video series on calculus 3 topics, and this time we'll be talking about triple integrals. So previously I talked about double integrals, but there are also triple integrals, which, as you might imagine, you have three integral signs. Basically you're integrating over some region, say D, and this region is a three-dimensional region. Some region in space, D, of some function of x, y, and z, dv, which is of course corresponds to the volume element, dv, tiny slice of your region. And so, a good way of thinking about this, because it's hard to visualize a function of three variables, because you need 4 dimensions to do that, it's hard to visualize, is you can think about functions like temperature, for example, which assigns a value, t, to each point in space. And if you wanted to add up all those temperatures, sort of like a summation of the temperatures, that's what the integral does. It adds up the temperatures, or whatever this f could possibly represent. And of course, it's very useful for finding averages as well. So if you wanted to find the average temperature in the room, you could create a region to be this whole room, a big sort of rectangular prism region, and integrate over that, and then what you do to find averages, basically you integrate dv, and then you divide by the volume. And this is a triple integral because it's a volume in 3 dimensions. And so this also works for calculating things like mass. You can say mass can be defined even as a triple integral of density, sometimes used for density, not at all, dv. This of course comes from the fact that dm equals dv, so you're just integrating dm really. Integral of dm equals m, like we were talking about before. It's a basic principle that the integral removes the d, just gives you back your m. Because of course we know density is mass over volume, the derivative of mass with respect to volume. If it's not uniform density, you want instantaneous density, or the density at an exact point. So if you knew your density function, you could integrate that over a region to get the mass. Similarly, we also talked about center of mass. You can find x bar as the triple integral of x is the average of the x values divided by volume. So there's an average for any function, you just integrate that function. So the average of x, y is the same thing, z is the same thing. Or if you want the center of mass of a region that actually has variable density, that's not uniform, then of course you would integrate is with density. You would get the integral of x dm over the mass instead of dv over the volume. And of course dm is really the density dv. So it's x times density dv, rho dv, over mass. So that's another average. And of course, in the most general form, if you wanted to combine x, y, and z together, we know that r, your position vector, is x, y, and z. So if you want your center of mass as a vector, you can just say it's the integral of divided by the mass. This is the average of all positions, all points, which is also going to be a triple integral as well. So dv divided by m, which is the mass. So those are several things you can do with triple integrals. So let's do an example to sort of see how this can be done. And let's take an easy function. F of x, y, and z, let it be x squared plus y minus z cubed. Z cubed x. Something like that. It's a random function. And we want to integrate this, say over a box-shaped region. 1 x. So say this is our region. I'm integrating over this little box here. Just like with double integrals, you want to sort of slice it into small regions that you're going to then integrate. So basically, the most common way we do it is we slice it into these sort of square slices. And then we say, well, the area of this, I mean the integral over this region, is the region R, is just the double integral over R of f of x, y, z for a given z value. So we fix a z value. This is the integral dA. And then we can integrate this whole thing dz as we change z. Or we can slice it the other way, or slice any other way really, in this case. Because it's just, well, these are easy functions. This goes from 0 to 1 in the x, from 0 to 2, and 0 to 3. So in reality, the final integral, that we all know how to do this, is dx dy. And the square is a 1 by 2 rectangle in there. And so this actually will be let's say we're going to do it this way. It's going to be, say, from 0 to 1 dx. And then y goes from 0 to 2. And z goes from 0 to 3. And then our function is x squared plus y minus z cubed x. So of course, we just do the same process that works from the inside out. So 0 to 1 dx, so the outside stays the same. X squared becomes x cubed over 3, plus yx minus z cubed x squared over 2. 0 to 1. So that would just be 1/3 plus y minus 1/2 z cubed dy dz. Now we do the same thing with dy. 2 minus 1/2 z cubed y. 0 to 2. So that's, we go from 0 to 3. That's this 2/3 plus 2 minus z cubed dz. And what is this? 2/3 plus 2 is 8/3. So when you integrate, it will be 8/3. Z minus z to the 4th over 4 from 0 to 3, which gives you 8 minus 3 to the 4th is 81 fourths, which is negative 49 fourths. And that's how you calculate it. But that was very simple, solid. So let's try to see how you would do it in the general form. In the general case, most of the time you would want to see which way is easiest to slice it. So in general, let's say we have some region, that looks something like this. This is our region D. Triple integrating of our function dv. This is D. So say it's bounded from below by this surface down here. And bounded from above by this surface right here. And you can see, let's say this is a function of x and y, g of x and y. And let's say this one is another function h of x and y. So what we would do here is you would be integrating these. First, you want to come up with a way to slice this solid. So first, you would consider these two functions. And so your inner integral would become integral from g of x, y to h of x, y of f, x, y, z, dz. Because that's where z goes. So the vertical component, which is your z component, so if we imagine we have a small slice here, at every point xy, some point xy here, and we fix this, we get a vertical slice, and we see when does z enter this region, and when does it exit the region. So how much will we actually be integrating? We're imagining a tiny little slice of dv is by adding up a lot of these little slices with respect to z. So this is the first part. We're going to be adding these up. So you want to see, when you're fixing the bounds, you want to see first where does it enter, where does it exit. Well, it enters in the bottom surface g and the top h for a given point to xy. After this given point, there's going to be a small region. And then, once you integrate this, you want to add up all these little things that there are. How many of these are there? Well, take this thing and say cast a shadow down here. This is the shadow of your region. Let's say it's R. So the shadow is all of the x and y values that you're going to be integrating over. So then you want to integrate this. So this thing right here tells you the integral of a vertical slice of this. And how many vertical slices do you have? Well, you have all of the ones that are in this whole region. So you're really going to integrate in this region dA. So this is a tiny piece of A. It's going to go up like this. So the dA times the dz, added up, integrated dz, will give you all these things here, and you integrate all of that throughout this whole region to get the whole thing. And just to finish the example, you can also divide this region, as we already know, as a double integral. You can fix your, let's say your lower and upper functions. Let's say this is, I don't know, P of x, and Q of x. You integrate, you want to further do it, you would integrate from here to here. For every x value that you fix, you would integrate from P of x to Q of x, whatever these values are. And then finally, you would see where the x begins and where it ends. Let's say it's a value a and b. That would be dy, and then finally the x values are dx. And you can drop the parentheses. Like again, there's always going to be numbers. These are always going to be numbers on the very outer integral, because in the end you're going to get a number which corresponds to the volume of this region. And this is, if you were slicing it vertically, you're going to start with z. So it would be zyx, or it could be zxy. Or in fact, there are other ways of doing it if your region is more easily done in other coordinate systems. But we'll talk about that later. Basically, for triple integrals in Cartesian coordinates, you want to find which functions are bounding it, g and h, and then look at your shadow of your region in the xy plane. Then try to integrate that. Let's say it goes from some function p to q, and then finally your x bounds a to b. And then that's how you do it. Or if this is rotated in any other coordinate system, you can do any other combination, dy dz dx, dy dx dz. And all the combinations are possible depending on which functions are easiest to use to have the proper bounds for the integral. So that's also an important thing to consider when you're doing this, is the order of integration. And that's basically what triple integrals are about. Thanks for watching, and I'll see you in the next video.